Okay, well, this is a follow-on to our computational exercise that we've done on molecular orbitals. And the piece of it that I just want to tell you about is how to calculate the bond order, and that's given by equation 9.2 in your text and described in section 9.7. The bond order, the idea is that the more electrons you have in bonding orbitals, that means that it's a stronger bond. But if you have if you have electrons in an anti-bonding orbital, then it's a weaker bond. And so the formula that I've kind of packed in here is the bond order is we take the number of electrons that are in a bonding orbital, psi is a shorthand for orbital, take away all the number of electrons that are in an anti-bonding orbital, and take that whole result and divide it by 2. So we're just going to take a few examples like this. I've drawn an MO diagram for H2, the molecule H2, and made out of a hydrogen with a single electron, another hydrogen with a single electron. That's why I put 2 electrons right there. And of course, since we haven't lost any electrons, that means I would say that the molecule has to have an electron configuration like this. We call this a sigma orbital, we call this a sigma star orbital, because this orbital is lower in energy than either the atomic orbitals that it came from. Then we understand that this must be a bonding orbital, because after all, it would require energy now to pull the molecule apart, because this electron would have to climb up to that energy, and so on. So sigma is a bonding orbital. Sigma star has higher energy than either the orbitals that it came from, so that's an anti-bonding orbital. So let's calculate the bond order here. I've got 2 electrons in a bonding orbital, so that would be 2, and then I don't have any electrons in an anti-bonding orbital. That means that's 0, so 2, and then I divide the whole result by 2, so I get a bond order of 1. So I'll say dihydrogen H2 has a bond order of 1. Okay? Now we can mess with this a little bit. What if I have the molecule H2, but I've taken away an electron, so it's H2 plus. Now what would that correspond to? Well, I need to take away one of these electrons here. So now I have this sort of electron configuration. One of these would have been not there. And, well, now I have 1 electron in a bonding orbital, still none in an anti-bonding orbital, so that means it must have a bond order of 1/2. Let's see, how about H2 minus? Maybe you would like to give this one a try. Okay, let's see how this would work. H2 minus means I have 3 electrons to work with, so 1, 2, and now the third one has to go up there. And so what do we have? I still have 2 electrons in a bonding orbital, those there. I take away 1 electron in the anti-bonding orbital, so that's 1. Divide the whole lot by 2, so that gives me a bond order of 1/2 again. Now I know that I've drawn this picture for H2, but it turns out it would look the same. Maybe the numbers will be different, but if I have a molecule like helium, He, helium there, He, okay, and let's see, helium has 2 electrons, so it goes something like that. And now I want to think about the molecule, the possible molecule He2. Well, let's see, I've taken 2 of those electrons and put them downstairs, but I need to have 2 more electrons, so I got to put them upstairs there. So what's the bond order in He2? Well, I've got 2 electrons in bonding orbitals, 2 electrons in anti-bonding orbitals. I get 0, so that means helium-2 has a bonding order of 0. Now, what does that mean? Well, what it means is that there's nothing holding helium-2 together as a molecule. And in fact, helium-2 does not exist in nature. You don't get helium. Now, one more little bit about this. What if I were to take away an electron from helium-2, so that would be He2 plus. Oh, that means I've only got 3 electrons to worry about, so I'm going to draw that like this, right? And, well, what's the bond order in He2 plus? Well, it's obviously 2 in a bonding orbital, 1 minus 1 in an antibonding orbital. That means 1 divided by 2, I get 1/2. So we would predict that helium-2, with the cation helium-2, would exist. That is to say, it's a real-life bond, and that molecule or that ion has a possibility of existing. Okay.